Oh, there you go. Let me begin with a word of prayer. So I'll start. Dearly Father, we thank you for today. Thank you for these students. I just pray that you just bless our work today. Thank you for our first week completed. Just pray that we'll be able to use the weekend wisely. And again, Lord, for your glory. In your name I pray, Lord Jesus. Amen. Okay, so any questions about homework or anything in particular? Alrighty, well, I'm going to show you how to integrate something here. So today we're doing integrals of trig functions, mostly. So I'll lead with something. Here's what we can do. Yep.
I don't remember if you did an inverse integral example.
Such as?
The integral of inverse sine of 2x.
Yeah, I did do something like that, but I can do another one. Let's see here. If I did a log integral, would that be okay? Or would that be helpful? Or you really need to see inverse? I mean, it's kind of the same animal.
Yeah, you did the log one.
I'm trying to find one here with bounds on it. Let's see here. So you want to see inverse sine of 2x, you said? Yeah, we could do that one. So this is still sort of this. When I think of integrals of trig functions, I'm mostly thinking of yowzers. Apparently I got an email. A little bit different things, but let's say, I don't know, integral from 0 to 1 of maybe 1/2 inverse sine of 2x. Still too much. Fine, I can't. Better not try to make up bounds at the moment. Okay, so this, what you're going to do is you let u equal to the inverse sine. You let dv be the dx, I think, and that'll do it for us. So let's see here. If u equals to the inverse sine of 2x, how does that differentiate? What's du equal to? 2dx over the root of what? 1 minus actually 2x squared, though. So there's maybe the thing. That'll do it. But it looks like, I mean, if you already doing that much, that's that's close, but no cigar. But not too far off, right? Let's see here, dx v is equal to x. And so that gives us x inverse sine of 2x minus the integral of 2x dx over the square root of 1 minus 4x squared. That's v du. Then what should I do, folks? Make a w substitution. I like that. Let's see here. W equals to 1 minus 4x squared. I thought that's what you said. Let's see here. Oh. Let's see. dw is then what? dw is minus 8x dx. So that means that minus 2x dx is equal to what? 1/4 dw. So I get plus integral of dw over the square root of w. There's a fourth out here, if I have done my arithmetic correctly. Given some of the errors I made earlier today, I wouldn't trust me. Let's see here. Let me let it. See, I've got a minus 2x dx to work with up there, right? I can trade it for a 1/4 dw, and then the root w. I think that's okay. So this is x inverse sine of 2x plus 1/2 the square root of w plus a constant, which is x inverse sine of 2x plus 1/2 the square root of 1 minus 4x squared plus a constant. One of you was itching for a real-world application yesterday, and I found just the thing. I just noticed this. Where'd that go? Number 58. The question is you're asked to well, you're given the mass density. So the mass density, I can't spell. Mass density, which is, by the way, dm dx, is given to be the natural log of x for 2 less than or equal to x less than or equal to 3. All right? And you're supposed to calculate the mass and the center of mass. For the rod with the given density. So I usually use lambda for a density, a linear density. In this case, the mass per unit length. I'm going to put my computer down before I drop it. I would regret that. My son has already dropped it enough. Okay, so how do you calculate total mass? I mean, what is this calculate mass, calculate center mass? How does that go? Well, we're given, right, that dm dx is the log of x, right? So what's that tell us? Basically, that tells us that the little bit of mass and the little bit of dx is what? It's the log of x dx, right? So intuitively, if you imagine a little bit of the rod like this right here, in this little dx, right, there is a dm. And how much dm? This much, right? And so to find the total mass, what do? You take the continuous sum of the dm, right? You add them up. We do this by integration. So m is the integral of dm, but what that actually means is to integrate from 2 to 3 log x dx. For example. Now, we figured out the integral of log the other day. What was it? Yeah, it was x log x minus x, right? I don't necessarily expect you to memorize that, okay? It's just convenient since we remember. You should be able to work that out like we did the first time, right? I think if you did a statistical analysis of tests I've given in Calculus 2, you'd find that log appears a significant portion of the time. It's just a nice entry-level example to see if people know what they're doing. Although I guess the deficiency of that example is most of you guys haven't memorized, now that I think about it. Hey. Anyway. So this is the fundamental theorem of calculus part 2, right? And so that gives me 3 log 3 minus 3 minus, parentheses are your friends, 2 log 2 minus 2. And how does that simplify? That's the natural log of 27 minus 3 plus 2 is minus 1, I suppose, minus the log of 4. So log of 27 over 4 minus 1 for what it's worth. You could use a calculator, I guess, if you really want to. Did I use a calculator? Oh, if a decimal makes you feel better, that's about or if you're Canadian, about 0.9095. in whatever magical calculus units we're working in at the moment. So what do you want it to be? Meet M is not for meters. It's an unfortunate confluence of events, but M is not for meters. Grams. How about solar masses? I mean, it doesn't matter, right? Megatons. That's very relativistic. Use energy units. I like it. All right, let's see here. Center of mass. So the idea of center mass, right, guys, is this is the center of mass, x center of mass. What you do is you take 1 over the total mass and you integrate x times the density dx over the object. This gives you the center of mass. This is the weighted average. This is the continuous extension of the center of mass formula you learn in physics, where you add, coordinate times mass plus coordinate times mass plus coordinate times mass and divide by the total mass. That gives you the average. It gives you literally the weighted sum. It is literally a weighted sum. I guess to make it a weighted sum, I would have to do this. Fine. There, you happy? Now it's a weighted sum. But we don't do that because it's dumb. So we take it's not quite a weighted sum, it's that. M times G is gravity. You will learn this soon, yes? Okay. You should know this actually, I think. Anyway, long story short. I say m, I should say little m. It's the little m we have up there, which I don't want to write down again. I'm just going to leave it as a constant. And we have to integrate what? X log x dx from what? From 2 to 3. Goodness gracious. I think we figured out the integral of x log x last time. That I don't remember. So I tell you what, we'll do it over again. So this is, I suppose we can make this the dv. We can make this the u if we want. So I have, so I've got x times x log x minus the integral, that's evaluated from 2 to 3, minus the integral from 2 to 3, v du. Oh! Why? Why did I do that? No. Don't do that. It's bad. Bad. I mean, it wasn't wrong, it was just not right. Let's see here. I've been told this is a rather pleasant color. Let's see here. So if you let this be, what do you want this to be? I think we want this to be u. Okay. So that makes this dv, right? So du is equal to dx over x, and v is equal to 1/2 x squared, right? So we've got 1/2 x squared log x evaluated from 2 to 3 minus the integral from 2 to 3, 1/2 x squared, right? Times du, which was what? Oh, it's the innocuous little dx over x. All right. So that's 1 over m, 1/2 x squared natural log of x. Oh, sorry, I got to evaluate this thing, right? I guess we can evaluate this while we're at it. What's that? That's going to be 1/2 of what? 9 log 3 minus 4 log 2. I'm with you on the 4 there. And then this integrates to what? The x's cancel, right? You're left with 1/4 x squared evaluated from 2 to 3. So 1 over m, 1/2 9 log 3 minus 4 log 2 minus 1/4 9 minus 4. Whatever that is. So, can you guys tell me where that number should be? So I think if you simplify that, you get 3/2 log 27 minus log 4 minus 1/4, by 5/4 rather. Blah, 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 blah. What was m? Oh, I wonder if I have a second here. Yeah. If I haven't made a silly mistake, I get 2.537 from this number. I might make an arithmetic mistake here or there, right? I hope that doesn't distract you from the calculus, right? What's the calculus here? You use integration by parts, right? You identify the problem for what it is. This is a center of mass problem, so that means that there's a standard integration that you have to do with the given data. To find the mass from the density, that's also a standard problem, right? Standard applications problem that now we know about. So. Any other questions? I think I'm going to get into the integrals of trig functions then, if you guys don't mind. Now, if you've, it's hard for me to know how many of you have actually watched the videos I posted over the summer. I know not many people watch them right away. From the views being at like 2 or 3 or 4 for a while. And it's hard for me to tell because I've got a lot of subscribers who just watch nonsense I post just to pass the time for no particular reason. I don't understand these people, but it's what they do. I mean, I've had a guy email, he's like, he's not really interested in math, he just likes to have some kind of like white noise on the background, and like, it's just perfect. So, I'm like, I'll take it. Sure, why not? So, I have not monetized my channel now. Although I have been harassed to try to like end every lecture with, thanks and please subscribe. But I refuse. Let's see here. Here's one that's kind of tricky. Let's start here. Now, you can actually do this with integration by parts. Do you want to see it? Or do you want me to let me show you the way that's the best way to do it? Best way, yeah. Okay. Both? You guys are wearing me out. I'm not sure I remember the integration by parts, but you got to try something like, you know what? I'm not going to do that. Let's see here. Best way. 1/2 1 minus cosine 2 theta d theta. So the best way to do this is to know trigonometry. This is the half-angle identity, right? These are things you should know, but you might not, but you must know soon, because I expect you to know them. Right, on the other hand, cosine squared theta is what? Can you guys think of anything else to add to this list? What's that?
Tangent squared.
Tangent squared. Okay, I'll take that to mean that you want me to write this down. We know that, right? We know that tangent squared theta plus 1 equals to... Oh, I did that wrong. I mean, sorry. It doesn't matter, but it matters to me. If you divide this by sine squared, you get... I'm an idiot. So these are... Yeah, just follow your heart. Something like that. These are popular, but there's more. I will add to this as we need to. So with that in mind, then it's easy to integrate, right? So this is integral of, theta over 2, d theta over 2, minus 1/2 the integral of cosine 2 theta d theta. So this, of course, is just theta over 2. And this, you can make a w or a u equals 2 theta substitution, right? So that's minus 1/4 the sine of 2 theta plus a constant. And there you have it. That's the integral of sine squared. Integral of cosine squared is pretty similar, right? You just have a plus instead of a minus. How about the integral of secant squared theta? Well, no one here knows?
1 plus the integral of 1 plus squared theta. X, but
Oh,
theta.
okay, yeah, sure. Would anyone care to tell me why I'm wrong? What does it mean to be wrong in here at the moment? I don't mean that he's factually wrong. In fact, what he told me is correct. It's wrong in the sense of we're making work for ourselves. It's wrong in the sense of this is one of the ones you're already supposed to know. You should not doubt yourself on this. This is what? Tangent theta. Thank you. So it's not a trap. I'm just checking. Because if you don't know this and you're trying to do something to integrate this, you're wasting your time. Right? So it's important to know the basic ones. Now, on the other hand, the integral of tangent squared, well, there, I'll take your advice, basically, which is to solve for tangent squared, right? This is the integral of 1 minus secant squared, right? Or, excuse me, secant squared theta minus 1, right? Sorry, there's a d theta here. That's a non-negotiable. The d theta must be written. If you don't write d theta, I will take off points. D theta is part of the integration. Secant squared theta minus 1 d theta, right, using the identity. And now, that's what? Tangent theta minus theta plus a constant. There you go. Now you feel like we actually did something, right? I know the previous example is kind of like, not very exciting. But I will ask that sort of thing on a test, on occasion. Just to see what happens. Okay, let's see here. How about the next thing would be something like integral of sine cubed theta. How would you do that? Yep.
Rip off one side, so because that we would have sine times sine squared, and that's the line we integrate.
Right, I like that. So I'm going to take your sine squared and raise you a 1 minus cosine squared theta. If that's okay. And I will do that because then I can make a u equals cosine theta substitution, and we're off to the races. Although I don't really do the races, so I don't know what I'm talking about. It's just something I heard. Anyway, let's see here. 1 minus u squared. And so that's like minus du. One more step for good measure. That's integral of u squared minus 1 du. Which gives us what? It gives us the answer. 1/3 cosine cubed theta minus cosine theta plus a constant. If you understand this example, you can easily do cosine cubed, sine to the 5th, cosine to the 5th. Pretty much any time you got some kind of odd combination of sine and cosine where like there's one of them left over, you can convert everything to like sine or cosine and use the rest of it to make a du with this kind of substitution, right? In my book, these are the easy ones. These are the ones I teach in Calc 1. right? They do come up in applications in here, so like you need to know them. When we do trig substitution, this will happen to you, these kind, on occasion. All right. How about this? Any questions about this? I guess I should number these examples. So this was example 1. This was example 2. This was example 3. Apparently this is example 4. Ah, my old friend. I miss one of her. So I tell you what, I'm nostalgic for this one. Integral of secant theta, d theta. Haven't done this one in a while. This one is not like the others. This one does not belong. So the way I'm going to solve this, I mean, I know ways to derive this with techniques in here, and I might show you some of those if you remind me. But the way I'm going to solve it at the moment is to make an obscure substitution. And the substitution I'm going to make is this. U equals secant theta plus tangent theta. Liate will not help you here, right? I mean, this is just a where on earth did this come from kind of substitution. You say, where did you learn this? I mean, how did you think of this? Well, I didn't think of this. My wife told me this. Where did my wife learn it? High school in Hong Kong, of course. And so, like, you know, I think that's how this gets passed down. Although my wife claims that this is reasonable if you just sit and play with secant for a while. So, yeah, whatever. Secant theta, tangent theta, plus secant squared theta, d theta. Lo and behold, you can factor out a secant theta there. You got secant theta times tangent theta plus secant theta by algebra. And so, look at that. What that says is that du over u is equal to secant theta d theta. So, kind of awesome. The way this substitution works is the integral of secant theta d theta is just the integral of du over u. Which is, of course, the natural log of the absolute value of u plus a constant, and there's your answer. This is one of those things I suggest is worth remembering in this course. You know, the answer here, you can just quote. I do expect you to be able to derive this if I say, make a u equals secant plus tangent substitution to show that the integral of secant is blah, you know, or to derive the integral of secant. That's something you should be able to do. You should be able to recreate the steps I did there. I don't necessarily assume that you would know to guess u equals secant plus tangent, right? But anyway, there it is. Now we already saw, it's kind of embarrassing, right? The integral of secant squared is utterly trivial, right? But the integral of the first power of it is a monster waiting to devour you, right? I mean, it's really weird. What happens at the third order? Yes?
I was going to ask that.
Ah, yes. That's the next on our list. Integral of secant cubed. So here's what we're going to do. We're going to say, okay, well, that's the integral of secant squared theta times secant theta d theta. Or maybe, excuse me, let me do that a little different. Let me put the secant squared over here, all right? Because that's, I'm thinking of this, right, as being a dv. I'm thinking of this as being a u, all right? So with that integration by parts, what do we get? Integral of dv is what? Tangent, right? So I get secant tangent. minus what? Minus the integral v to u, which is what? Tangent. And then, well, du is kind of a drag. It's secant tangent. Right? I should have told you to buckle in. It's about to get loopy. Let's see here. That's a tangent squared, right? So what can we do with tangent squared theta? Well, tangent squared theta, remember, we can do what to that? We can say tangent squared theta is secant squared theta minus 1, right? And you see, so what this becomes then, in view of that identity, you got your secant theta tangent theta minus, let's see, tangent squared again was secant squared theta minus 1. So minus the integral of secant cubed theta, because secant squared times secant is secant cubed, plus the integral of secant theta d theta. Just to emphasize here, I'm taking this tangent squared, I'm using this identity here, and I'm breaking up the integrals. But we, oh, hey, we already know something there, don't we? I mean, we just figured out this character up there, right? So I can rewrite this as secant theta tangent theta plus the natural log of the sum of secant theta plus tangent theta minus the integral that we're interested in. See, because this is minus secant cubed, which is what we started with, but with a minus. And so you solve for the integral, and you're done. It looped. Add I to both sides, and that will give us the answer. Now, there are these recursion formulas, all right? Like if you attack the integral of the nth power of secant and you integrate by parts on it, I think you can derive these formulas which link the nth power to other powers. So these recursion formulas are maybe another way to attack these things, but I'm as interested in the journey as I am the answer here, all right? The point of this is not just to find what's boxed in purple there, it's to try to understand the calculational steps we're doing, how we're doing them, you know.
So can you go over when you split the integral again from tan squared to secant? Tan squared should get, and then you went.
Yeah, the step I haven't written down is this one. So when you distribute this, it gives you a secant cubed minus, and the minus times minus gives me a plus secant theta d theta. So, uh-huh. Let me take a look-see in the book, see if I can come up with something else here to show you guys. Sine cubed, sine squared, cosine cubed, cosine squared, sine cubed, cosine cubed. Ooh, sine cubed, cosine cubed. That looks fun. Let's do that one. Let's see, where are we? We're on example 7. Sine cubed theta, cosine cubed theta, d theta. I mean, you got choices here. I think I'm going to split off a cosine. So this is like integral of sine cubed theta, cosine squared theta, cosine theta d theta. So what I'm doing here, I've basically decided this is going to be my du. Right? In other words, I'm going to make my u equal to what? If cosine theta d theta is my du, I'm just sine theta. I mean, you could try that too, but if you make like a u equals sine cubed or something, then that might even work here, because you got, well, but then I need like a 3 sine squared theta somewhere. It's not hopeless, but let's see here. So I do that though, but then if I do that, I have to convert all this stuff to what? To sine thetas, right? Well, that's half done, right? Or maybe it's 60% done. How do you count it? I don't know. But sine cubed theta, my cosine squared I can trade for 1 minus sine squared theta, right? And then that's the differential of sine theta. This notation I just used, you can use it if you understand it, and if you don't, it doesn't matter that much. But that's an implicit substitution notation. You write differential of the substituted variable that says I'm integrating in that. I've kind of undone the usefulness of this by writing u equals whatever up here. But anyway, so what do you have? So this is the integral. I'm going to go back to the u formulation. So this is u cubed minus u to the 5th, right, du. And so you got yourself 1/4 u to the 4th plus, or rather minus 1/6 u to the 6th plus a constant, right? And okay, so that is 1/4 sine to the 4th theta minus 1/6 sine to the 6th theta plus a constant. And there you have it. Like I was saying, if you really understand the example we did with sine cubed, it's essentially the same trick, right? Same idea. Now, if you have a net even power of sines and cosines, that's more of a pain, right? For example, if I face the integral of sine squared theta, cosine squared theta d theta, well, let's see, there's a couple different ways to go here, but I'll show you the stupid way to start with. So this is 1 minus cosine squared theta times cosine squared theta, cosine squared theta d theta, which of course is the integral cosine squared theta minus the integral of cosine to the 4th theta, right? The first thing we already know how to do. Well, maybe you don't know yet, but you should learn soon. I mean, we use the half angle identity that I wrote over here. The other one, though, is what? Cosine to the 4th is what? It's 1/2. It's cosine squared squared, right? So that's 1/2 of 1 plus cosine 2 theta quantity squared. It gives me no joy to rewrite this 15 times, so I'm just going to call this thing Pac-Man. So that's Pac-Man. And then I have minus 1/4 the integral of, oh my goodness, 1 plus 2 cosine 2 theta plus cosine squared 2 theta. By, as usual, algebra. Dr. Cook, I understand the calculus. I just have trouble with the algebra. Yes, I know. That's the point of this course, actually, is to learn how to do algebra with confidence, clarity, and precision. It's not really about calculus. That's a secret. I'm telling you, but that's the truth. Right? If we just cared about you finding answers to calculus questions, we'd just teach you Mathematica. Right? Just like if we just cared about you getting from one side of the town to the other, we'd just sign you up for Uber and you would just get in the car and it would take you to the other place and you'd be done with it, right? But if you want to learn how to jog or how to run or whatever, I know this doesn't make sense with me saying it, but you have to train to build muscles. And the same with algebra. That's what this course and the calculus sequence is for in large part. Because you guys did not learn algebra in algebra. How do I know this? The quiz, I guess. Life experience. I am, of course, not speaking to every last one of you. Some of you actually do know algebra. But statistically speaking, we have a problem with math education in this country. I don't know. Anyway, maybe in the world. I don't know. I see evidence for it being different in other places. Anyway, I digress. So why did I do that? Well, some of these things we can do, right? And that's like minus 1/2, so that's actually being 1/4 sine of 2 theta. And then what? Minus 1/4 the integral of cosine squared. What does this become, though? That's really 1/2 of what? Again, use some color coding here. I just straight up integrated these things down to here. And at the moment, I'm still fussing with the cosine squared 2 theta. What you got to do is envision this identity for beta instead of theta, for example, right? And put beta equal to 2 theta. What happens? Yeah, 4 theta. Exactly. And so we have Pac-Man, which I'll eventually calculate. Actually, let me call this whole thing Pac-Man tilde, as to stop writing it. I'll write it again later. So minus 1/8 the integral of what? 1 plus the cosine of 4 theta d theta. And so you got yourself a Pac-Man tilde minus 1 theta over 8 minus 1 over 32, making a u equals 4 theta substitution. Sine of 4 theta plus a constant. You mean to tell me that we're going to be doing u substitutions in here without writing them, just doing them in our head? Yes. That is what we're going to be doing. You are allowed to do that too, but you should do it correctly and when you need to, right? Okay, anyway. Let us unwrap the Pac-Man tilde, which was what? To start with, Pac-Man should have been what? Theta over 2. Plus 1/4 the sine of 2 theta, integrating that cosine 2 theta term. And then I've got the Pac-Man tilde junk, which was minus theta over 4, minus 1/4 the sine of 2 theta, minus my theta over 8 minus 1 over 32. Why did I do this example? Because it's important for you to see it. You know, if I just do easy examples all day, it doesn't help you when you actually have homework, which is hard. So you can simplify this, right? You got theta, you got theta, you got theta. You get a half minus a fourth minus an eighth. What's that work out to? In other words, 16 30-seconds minus 8 30-seconds minus 4 30-seconds, which is what? 4 30-seconds? I think is it theta over 8? I don't know. Maybe it's theta over 8. Did you get theta over 8? Oh yeah, this is 4/8 minus 3/8, right? So yeah, theta over 8. How many sine thetas? Ah, hey, cool. And then minus 1 32nd. Now, is there anybody here who's been screaming silently in your chair the whole time because you knew a better way to do this? Where no one feels as strongly about integration as I do. Yes, what?
We have a sine theta, cosine theta is sine 2 theta.
Ah, yes. Indeed. See, he is not subject to my subterfuge because he is aware of the identity, which is that sine theta cosine theta times 2, right, is the sine of 2 theta. So this integral I could trade for an integral of, in fact, sine of 2 theta over 2 quantity squared from the outset, which is way easier, isn't it? So this is 1/4 the integral of sine squared 2 theta d theta, which, if you'll forgive me this vertical work, 1/8 the integral of 1 minus the cosine of 4 theta, again using the double angle formula. On a double angle, it gives you a 4, you know. And then there it is, theta over 8 minus 1 over 32 sine of 4 theta plus a constant. I don't know about you, but I think that knowing trigonometry and being aware of where you can use it might save you some work. Right? A sobering lesson. I don't know why I did that. I mean, why did I do that? Because there are other problems where this trick doesn't help you, right? If you just face, for example, it's pretty easy to see this example we just did. It shows you how to do like this in isolation, right? This is how you have to do the integral of like cosine to the 4th or sine to the 4th. It's a double angle identity followed by like squaring the double angle. 2 applications of the double angle identity, one after the other, you know. But yes, this is obviously the like smarter way to do it, right? Is there other trigonometry that could help us out with other problems? Certainly, and I'll probably do some more of that Monday. So have a good weekend, guys. Oh, wait a minute. Monday we have a quiz, yes. So.